Hello everyone and welcome back. Today is our third and final video talking about how integrals can be applied to study the motion of a moving object. 2 days ago we were talking about how the indefinite integral was used to find velocity from acceleration and how to find position from velocity. And then yesterday we were talking about how the definite integral can be used to find displacement and distance traveled for an object that's moving in one-dimensional space. Today, we're going to be talking about how the definite integral can be used to find distance traveled for an object moving in two-dimensional space, not necessarily along a straight line, but potentially along a curved path. Now, for an object moving in two-dimensional space, the definition of displacement and distance traveled changes just a little bit. If you have an object that moves in two-dimensional space from a point A to a point B, following this dashed blue path in this picture, then the displacement is the distance between the initial position and the final position, just the straight line distance between your start point and your final point. Meanwhile, your distance traveled is your actual distance traveled, accounting for all of this movement outside of the straight line between A and B. Distance is just your total distance traveled along this curve. So in other words, in two-dimensional space, sort of the major difference between displacement and distance is that displacement treats the movement as if it were in a straight line. Directly from A to B. Displacement, once again, does not account for sort of the reality of the journey that was required to get from point A to point B. Displacement is treating the movement as if it were just a straight line from A to B. The real difficult quantity to calculate in these examples, in my opinion, usually is the distance. How would you find the length of this blue curved track that the object has followed? Now for an introductory exercise, once again, a little baby exercise to help us to get our thinking correct. Suppose that the object did actually travel just in a straight line forward from an initial position of -3, 4 to a final position of 1, 2. If the object did move in a straight line, what would be the total distance traveled by that object? Well, in that situation, if the object is moving in a straight line, you can find the total distance traveled just by using the distance formula. So what I am going to do using that distance formula is I am going to go in and take the difference of the final x and the initial x. Square that, and take the difference between the final y and the initial y and square that. And the sum of those two squares, square rooted, would be the total distance traveled by the object. Now I'm going to make a note. Here I have used the specific values of 1 for x, -3 for x, 2 for y, and 4 for y. But in general, of course, this is your final x value minus your initial x value. This is your final y value minus your initial y value. Or put even one other way, this is the difference between your x's, the space between your x's, a change in x, a delta x, and over here is a delta y, a delta y. So this is really quite interesting. What we have just written down is that the distance formula is equal to the square root of delta x squared plus delta y squared. Okay, this is significant. Go ahead and keep that in the back of your mind, this thing right here. Now, This was a toy example of an object that is moving in a straight line, but what if the object is not moving in a straight line? What if the object is moving along a curved path? How can I take this idea and extend it to a situation where the object is not moving in a straight line? So in this scenario, we have an object that is moving in two-dimensional space, and as is our tradition, we are going to start by thinking about what if we had a table of data that told us the object's location, horizontal and vertical position as measured at certain periods of time, in this case every 5 seconds. So at the initial time, the object's position is 1, 2. After 5 seconds, the position has changed from 3, 0. After 10 seconds, it's now 5, 4. And after 20 seconds, the object's position is now negative 1, 1. So if I used Desmos to generate a picture showing the object's location at each of these given times, then the picture would look a little bit like this one. The object started in this location right here, which is 1, 2. And then it traveled to this position down here, 3, 0. Now, did it actually travel from 1, 2 to 3, 0 along a straight line? I have no idea. It's very possible that during that 5-second window of time, that this object, moved around all over the place and did all kinds of stuff, getting from this one point to the other. But I don't have any information about what the object is doing between time 0 and time 5. So again, as usual, I'm just going to make a simplifying assumption. I'm just going to assume that the object did the simplest and easiest thing and traveled in a straight line between those two times. Because if I make that assumption, I can then calculate the total distance traveled between those times using the distance formula. Likewise, even though I don't really have enough evidence to justify this belief, I'm just going to assume that between time 5 and time 10, the object traveled in a straight line from this point 3, 0 to this point 5, 4. The object could have been doing all kinds of stuff between those times and twisting and turning around, but I don't have enough information to say one way or another. And in the absence of that information, I'm just going to assume the simplest case, which is that the object moved in a straight line between those 2 points. And once again, I'm going to pretend that the object moved in a straight line between this third position and this final position down here at -1, 1. I'm going to make that assumption because it just makes it possible for me to do the calculation, or at least an estimation in this situation. So now that I have split up this object's journey into 3 separate pieces, and I've treated the object as if it were moving on a straight line between each of these 4 checkpoints, I'm going to use that assumption and I'm going to use the distance formula in order to calculate, or at least estimate, total distance traveled by this object. So what am I going to do? I'm going to add together the total distance traveled, which is the change in x squared plus the change in y squared. I'm going to add together all of those straight line distances for each of these 3 legs on the journey. Now, this is the moment in these questions where I usually pause and I say, what would this look like as an integral? But what we've written down so far already is already very different from the other integrals that we have come up with in our other applications. Compare what we have here to what we got, for example, yesterday. In our applications yesterday, when we wrote down our Riemann sum, we got, for example, V of Ti star times delta T. So chop, multiply, and add, and then that symbolic notation became integral function dt. Likewise here with the speed function, chop, multiply, and add, we had absolute value times delta t and then the sum. And then that could turn into integral absolute value v of t dt. Let's also roll back to when we did this for center of mass. When we did the center of mass calculation, we had the sum rho of xi star times delta t. So chop, multiply, and add. Same thing was true down here when we did center of mass. Chop, multiply, we had a times delta x, multiply, and add. So the major difference between these previous examples and what we've got in front of us right now is that we've got the chop, we've got the add, but we don't have the multiply. We don't have a times delta x over here in this expression. So that's the first thing about this, which is really quite strange. The other thing about this expression, as it's currently written, that's strange, is that we have sort of two delta quantities, a delta x and a delta y. And that's different from all of these other examples, where we had just delta t, just that one delta quantity, and this example with center of mass, where we had just delta x. Now I'm going to do an algebraic manipulation that is going to fix both of those issues in one maneuver here. I am going to go ahead and factor out a delta x squared from under the root. Now, if I factor out a delta x squared from under the root, then the square root of delta x squared will just become delta x on the root's outside. If I factor out a delta x squared, then delta x squared removed from delta x squared will just become 1. And if I factor out a delta x squared from this second term under the root, then I will get delta y squared divided by delta x squared, or in other words, delta y over delta x, both of those guys squared. Aha! So now I have an expression that looks a lot more similar to the kind of Riemann sums that I am used to. By factoring out a delta x squared from under the root, I have now got the chop, I have got the multiply, and I have got the add. And if I asked myself, what would this become if I had a lot of data to turn this into an integral? Now I can say the sigma would become an elongated S. As the space between the data points got smaller, the delta x would become a dx. And as the space between the data points got smaller, the delta y would also become a dy. So I would have dy over dx quantity squared under that root. Aha! Do you recognize this fellow right here? Dy over dx? That's the derivative. That is the derivative of y with respect to x. So as an integral, if you want to calculate the distance traveled in two-dimensional space, what have we just figured out? If you wanted to do an integral for distance traveled in two-dimensional space, you would have to integrate from your smallest x value to your largest x value, the square root of 1 plus the derivative of y with respect to x quantity squared times dx. And that's just a result of taking the distance formula from 2D and factoring out delta x, and then letting the space between the data points get smaller and smaller. So now that we've made a note of this, let's go ahead and finish this problem using a Riemann sum estimate. Going ahead to calculate the lengths between each of these checkpoints in our table. We have the distance between 1, 2, and 3, 0. we have the distance between 3, 0 and 5, 4. And then we finally have the distance between 5, 4 and -1, comma 1. So this expression, the sum of these three lengths, would be an estimate for the total distance traveled by this object, and you can get the sort of estimated value in a calculator. Looks like that is about 13 units of length, which feels right based on the picture, about 13 units of length in total. Seems reasonable. Okay, so once again, the entire point of this exercise was to give us practice figuring out what kind of integral to set up to get started calculating a real world quantity using the techniques of Calculus 2. And so now that we've gone through that thought process, let's make a final note about what this formula does and how it functions. So someone says, I'm thinking about an object which is traveling along a curve in two-dimensional space. And let's suppose that f and x are related by some function, which I'll call f of x. Y is equal to f of x. So that's the relationship between the vertical position of the object and the horizontal position of the object. Let's also suppose that as this object is moving, it is moving between x values that at the smallest are a and at the largest are b. In this case, the integral formula for the distance traveled by this object in two-dimensional space is the integral from the smallest x value to the largest x value, the square root of 1 plus the derivative of y with respect to x squared, and then dx to close that. This would be the integral formula for distance traveled along a two-dimensional curve. Finally, let's get some practice using this formula to do a calculation. Someone says an object is traveling in two-dimensional space, and the curve on which it is traveling is represented by the function y equals x squared, and it's traveling between at the smallest x equals -1 and x equals +1. Let's try to find the total distance traveled by the object. So going out to Desmos, here is a little picture. This object is traveling along this curve or along this track represented in red here. So let's go ahead and try to find the total distance traveled by this object using an integral. According to this distance traveled formula up here, if I wanted to calculate the distance traveled for this object, I would just have to integrate from -1 to +2, from the smallest x to the largest x, the square root of the derivative of y with respect to x. Now, if y is equal to x squared, can you tell me what is the derivative of y with respect to x? Well, the derivative of x squared is just 2x, so that would be what dy dx is equal to in this case. So plugging that in to our distance traveled formula, under the root we have 1 plus distance derivative squared, and then we close that with that little dx, which is what happened to our delta x as the gap between the data gets very small. So now that we've set up this integral, let's think about how we would actually calculate this integral. So once again, I'm looking at this integrand, and I'm trying to think of what can I possibly do to find the value of this definite integral. The first thing I'm going to check, odd function rule. Can I use it? No, I cannot, because the limits of integration are not exact opposites of each other. Second thing I'm going to check, can I think of a nice antiderivative for this function? And the answer is no. Right now, we do not have any antiderivative formulas to help us with a square root that has something really complicated underneath. Next thing I'm asking myself, can the area underneath this function be calculated by a very simple geometric formula? So let's go to Desmos and let's see if the area underneath the function that I am integrating, 1 plus 4x squared, something that I have a geometry formula for. But I think the answer to that question is no. The area underneath the function I am integrating looks like a pretty unusual shape. So is there any way I can break this integrand down into simpler pieces? No, I cannot think of a way to do that. If I simplify this integrand, does it become easier to find the antiderivative? Well, I cannot simplify this integrand at all because you cannot simplify square roots that have sums underneath them. So because I have no antiderivative that I can find, I have no symmetry that I can use, I have no geometry that I can use, as usual, I'm sort of forced into calculating this definite integral using a Riemann sum estimate. So as usual, in a situation like that, I have to create my own table of inputs against the values of the function that I am integrating. I have to make my own decision about how far apart I want my data to be spaced. For simplicity's sake, I might decide a delta x of half a unit. Then I have to plug all of those values into the function that I am integrating, and I have to calculate those outputs. So stand by as I do that on the side. And now that I've plugged those values into the function that I am integrating, in order to fill out this table, all I have to do is set up the appropriate left or right Riemann sum. Again, I'm just going to go with left for no good reason, where I have the left output times the delta x, where I have the left output times the delta x, where I have the left output times the delta x, and so on. Okay, and now that I've written down that Riemann sum, that left Riemann sum, let's go ahead and get an estimate of the value. And according to my calculator, this is roughly speaking 5.7 units. Again, that feels right to me. If I go back to the picture that showed me the track of the object's movement, this picture of y equals x squared between -1 and 2, yeah, it feels about right that it was roughly speaking 5 to 6 units of movement. Yeah, that feels approximately correct. Now, one thing that I just want to warn you about, it can be easy to get confused between the two pictures that we have been looking at and the two functions that we have been working with in this problem. The function y equals x squared is the function that tells you the arc of the object's movement. It's telling you the path along which the object traveled. But x squared is not actually the function that we are integrating. The function that we are integrating is not x squared, but this function that we sort of set up ourselves, which is square root of 1 plus 4x squared. This is the function that we are actually integrating. This is the function where the area underneath this function, represents the total distance traveled, as opposed to this function whose arc length represented the total distance traveled. So just be careful. It can be confusing when you have two different functions in a problem like this that are serving two different purposes. Now, as a final heads up, I just want to draw your attention to the fact that the formula that we just found for distance traveled in 2D is the same formula that you could use to calculate the length of the curve y equals f of x, what textbooks often call the arc length. Because as we noted, the this picture here, the length of this curve, the length of this arc, is an exact match to the distance traveled by an object that is following this curve, that is following this track. So just bear in mind that if someone is asking you for the arc length of a curve, then you can also use this exact same formula to calculate that result. Okay, and that concludes today's video talking about definite integrals as they apply to two-dimensional motion.